Hi, everyone. I'm Yusheng from USENIX presenting our work on a safe and efficient use-based extension framework. Extensions are everywhere in modern software. Extensions allow us to customize software for different deployment needs without modifying the original application source code. It can be used to add new functionality, modifying behavior, or integrate with external systems. People use extensions instead of modifying the source code because it's easier to maintain and update their systems. Take Nginx as an example. Different Nginx deployments need different extensions. Some need firewalls to block malicious requests, others need load balancer to distribute traffic, and many need monitoring for observability. Consider a user wants to deploy a firewall extension to block malicious requests. Here is how the firewall extension execution model works in Nginx. Before deployment, the user writes the firewall logic using Nginx APIs and associate the firewall with request processing extension entries. During runtime, when Nginx reaches the request processing entries, it jumps to the firewall extension. The firewall executes in the extension runtime execution context, analyzing the request and deciding whether to block it or allow it. Extension frameworks need three key features as shown in the figure. First, fine-grained safety interconnectedness trade-off. Extensions need to interact with the applications by reading data and calling functions. For example, a firewall extension needs to read request headers and decide whether to block or allow the request, while a monitoring extension needs read-only access. However, allowing too much interconnectedness comes with risks. Real-world incidents show production outage from safety violation in Nginx, Apache, and Redis extensions. You can see our paper for more detail. Shows system managers want to specify safety interconnectedness trade-offs that allow only a minimum permission each extension needs. Second, extension frameworks need isolation to protect extension from application bugs and vice versa. We use extensions to provide safety guarantees, so isolation is paramount for correctness. Third, efficiency. Extensions often run on critical paths where every millisecond matters for user experience, so we need them to be fast. Unfortunately, existing approaches cannot satisfy all the requirements at the same time. Dynamic loading and native execution achieves better speed by providing no isolation or fine-grained safety and interconnectedness trade-off policies. Software for isolation systems like WebAssembly and Lua deliver safety but carry 10 or 15% performance penalties. Sub-process isolation ensures separation but has higher IPC overhead. We also noticed eBPF in kernel can also be used for user-based extensions. But kernel eBPF uprops offer isolation but trap into the kernel on every invocation, making it less efficient. So we present a two-part solution that addresses all the three requirements. First, to help navigate fine-grained safety interconnectedness trade-offs, we create an extension interface model, or EIM, to solve the interface problem. EIM treats every extension capability as a named resource and uses a two-stage specification approach. Second, we create bpftime, a new use-based eBPF runtime that provides efficient support for EIM and isolation. It uses three key features: eBPF verification for zero runtime safety checks, MPK for isolation, and concealed extension entries that reduce performance overhead. Together, they provide safety with efficiency while maintaining the eBPF compatibility with kernel and existing eBPF tools. Our evaluation on 6 real-world applications shows bpftime achieve all the 3 requirements: fine-grained safety control, strong isolation and efficiency with up to 6 times better performance compared to solutions like WebAssembly. Now let me discuss the motivation of the problems and the challenges. Let's get into the EIM part, which is the interface. The goal of EIM is to enable fine-grained trade-off between safety and interconnectedness. This is a challenge because the safety interconnectedness trade-off are per deployment decision. It depends on where the person deploying the systems, like the system admin or the extension manager, wants to enable or choose. But the person deploying the system is not the developer of the system, so they lack application expertise. They don't know what extension features should be allowed by the application. EIM tool for this challenge is a two-phase specification. We model all the resource as capabilities and split the process into the development phase and the deployment phase. It works like this. During development, the application developer who understands the host application's internal details define the possible interaction points for the extensions. They create a development times EIM spec, which lists all functions an extension could call or data it could access. Before deployment, the extension manager who understands the specific need of a deployment is responsible for security and configuration. They review the capability offered and create a deployment time EIM spec. This spec grants the minimal set of privilege and extension actually needs to do its job, following the principle of least privilege. Finally, when the extension is deployed, the extension runtime uses the deployment spec to verify that the extension only performs allowed operations. This ensures the policies are enforced at runtime. This is a simplified version of our model. You can see more details on our paper with all the 4 rules, including the extension developer and finally end user. Now let me show you how EIM works in practice using Nginx as an example. During development time, Nginx developer annotate their code to declare what extension could possibly do. They can add a state capability called read-PID for accessing the process ID, a function capability Nginx time for getting timestamps, complete with pre- and post-hold logic condition, and extension entries like process begin when request process starts. This annotation can be put into the code, compared into the binary, and automatically extract. This happens once during development and create a complete map of what extension can access. The key insight is that developer only declare possibilities. They don't decide what actually get used. At deployment time, the extension manager writes simple YAML policies that grant minimal privilege to each extension, enabling fine-grained safety interconnectedness trade-off. For example, an observability extension might only request data and call login functions, where a firewall extension needs both read and write access to modifying the response. This policy lies completely outside the application code. You can address the safety interconnectedness balance per extension without recompiling the policy's technical comeback, like in 30 lines of YAML. In the next part, I will introduce our new userspace eBPF extension framework called bpftime. Our goal here is to efficiently support EIM and isolation for userspace extensions. Now you might ask, can we just use existing frameworks like WebAssembly extension frameworks to enforce EIM policies? You can try to implement EIM on them, but unfortunately, as we discussed in previous work, current framework use heavyware technologies for safety and isolation, which introduce significant performance overhead. So our solution is a new design that combines verification, binary writing, and hardware features to enable efficient intra-process extensions. We are using eBPF here because it provides verification-based safety and a rich ecosystem we can reuse. Let me walk you through how we achieve this with the bpftime framework. First, an eBPF application, same as kernel eBPF application, acts as our extension. The eBPF application is first running on the bpftime loader. This loader includes a verifier that performs verification for efficient EIM support. By tracking the eBPF code against the specification before execution, we can enforce our EIM policies with zero runtime overhead. To maintain isolation between the host and the extension, we use hardware features like MPKs. This prevents extension from accessing unauthorized memory and protect a host application from bugging or malicious extensions and vice versa. For invoking extensions, the CL extension entry uses battery writing for efficiency. Instead of heavyware hooks, we patch the host application with lightweight trampolines that redirect execution to the extension at the right moment. This is similar to how kernel eBPF hooks works, but entirely in userspace. As you can see, the host application and the extension runs in the same process, which enables intra-process extension for efficiency, in eliminating cross-process communication costs. Finally, our entire framework is compatibility with eBPF. Existing eBPF applications and tool chains works with the bpftime out-of-box. This compatibility also allows userspace extensions to communicate with kernel space eBPF programs. You can write one program that can run partly on userspace and partly in kernel, enabling powerful full system of observability and control. Now let me show you how bpftime works in practice and our evaluation results. As a userspace eBPF runtime for observability, network, and GPUs and general extension framework, bpftime is open source on GitHub with an active community with like thousands of stars and many users. We built 6 real-world applications to demonstrate how people are actually using it. First, we use extensions to customize applications, including a Nginx firewall, a Redis optimization, and a fuse cache. Second, we use extensions for observability by adapting existing tools like Gitflow, Syscon, and SSR-Smith. Some examples here are partly running in kernel, partly running in userspace. You can find more details in our paper, but due to time limit, I will focus on just 2 examples. We implement an Nginx firewall with EIM and bpftime and compare it with different extension approaches. In the diagram, higher is better. Lua and WebAssembly extension impose 11 or 12% throughput loss. That's significant overhead that many operators can't accept in production. Plus, these older methods don't let you control safety and interconnect trade-off like EIM does. bpftime achieves only 2% overhead, that's a 5-time or 6-time improvement over existing approaches. Then we use bpftime for SSR-Smith, which monitor encrypt TLS traffic as part of the BCC eBPF tools and compared to kernel eBPF. We run SSR-Smith on an Nginx deployment to test different data sets from 1,000 bytes to 200 bytes. The y-axis shows throughput where higher is better. You can see the performance difference is more clear with less data sets. With kernel eBPF, the monitoring costs 28% throughput loss. That's too much overhead for production use. With bpftime, the same monitoring functionality costs only 7% overhead. In summary, our contributions are EIM and bpftime. EIM enable fine-grained safety interconnect trade-off. They allow you to specify less privileged policies without touching application source code. And bpftime support efficiency, safety, interconnect trade-off, and isolation with nearly native performance using offline verification, inter-MPK, and dynamic binary writing. Also, as you can see, bpftime is fully compatible with the eBPF ecosystem. You can get started by running as a drop-in replacement for eBPF commands. bpftime is open source at GitHub. You can scan the QR code to see. I'm happy to take your questions. Thank you for listening.